to get a rough idea of where the room sits, and of course I'm biased, so I'm going to say one thing. Let's get a show of hands for each one. How many people think AI is going to be the biggest business impact in the next decade? What about blockchain? Quantum? I think there are a few people who didn't vote there. My pitch to the AI people, because that's obviously what's getting the most talk at the moment. In 2015, AI sort of looked exactly like quantum does at the moment. You had real machines, you had potential, but you had limited people who could actually program them at a high level. And then blockchain, that's a fair statement. Private investment hasn't exceeded blockchain in the quantum realm ever. But if you take government investment, quantum public investment is way higher than blockchain ever has been. You've got people like Nvidia, BlackRock, sovereign wealth funds investing in quantum. So either all of the most conservative financial people are making a terrible decision, or most people haven't really looked closely enough yet. A little bit of background into me, because I think it helps to contextualize why I'm here, because I'm obviously quite young. I'm a third-year comp sci student. I grew up obsessed with Iron Man. I watched Iron Man when I was 7. I was really blown away by all the cool tech, and I'm like, that's what I want to do when I'm older. But I was always really frustrated that we sort of live in this period of time where everything has been, well, it seems like everything had been discovered from a naive kid's perspective. You know, all the countries have been conquered. Space is a little bit far away as far as our timeline is concerned. You've got people like Einstein, Newton, who've discovered all these foundational physics principles. Where do we carve our way in pioneering the next step for humanity? And when I came across quantum physics in high school, when I was bored and looking for something to do, I was like, this is so confusing, and this is obviously where the most pioneering research is going to be done. So I tried to get into it. I read pop science articles, which don't explain things particularly well. They're sort of inaccurate. So then you try to take the next step, and then you just fed research articles with really high level maths and physics that there's no way you can understand as a high schooler. So for people who just want to get into quantum programming, who want to start building, which is what the industry desperately needs, there's no on-ramp. So I built the way in. So I'll introduce you to Qubit Forge. I'm not here to pitch you, but we will be using it tonight, so I'll sort of introduce it a little bit. You solve real quantum coding challenges in the browser. You can sort of think of it a little bit like a LeetCode for quantum. There's XP, there's medals, there's a leaderboard. We passed 200 users this month. We released it in May. And then I've already talked about PsiQuantum. But yeah, there's a real demand for hiring in the area we're in. So does everyone have their laptops out? Hop onto that website and put that code in. Hopefully it works. I haven't run one of these before, but hopefully it all goes smoothly. Yippee! The lobby actually works. This looks suspiciously like Kahoot. I promised I didn't rip off Kahoot.
Yeah, you got yourself a waiting track for when people are solving the problems.
Yeah.
Been crashed since the last recording.
No, it looks fine to me at the moment.
Good. Still.
It's sort of just flopping around.
No, I was talking about power because it's still got the red blinking light. And...
Yeah, that's frustrating. Is there anyone that's still waiting to get in? If not, I'll move on. All right, so I'll sort of provide, like I'll kind of show you something. I was planning to have this on the demo section, but I realized it's not, so I'll just show it to you. This is the sandbox, so you can sort of drag stuff in here, run stuff, and sort of build an intuitive understanding for how it maps to probabilities, and you can sort of see the code of a quantum circuit. But I won't spend too much time on this because I want to sort of get into stuff that you guys can actually do. So before we do that, I'll sort of teach you the first thing you need to know to get started with the first challenge. So what is a qubit? Nielsen and Chuang, which is practically the Bible of quantum programming, explains it this way. A classical bit is like a coin. It's either heads or tails up. So your entire computer is filled with billions of coins. I mean, it's not, but you can imagine that it's filled with billions of coins. And they're all sitting flat on the table. They're either a 0 or a 1. And then if you think about a qubit, what makes a qubit different to a normal bit is you've now got a spinning coin. So the coin is neither 0 or 1. It sort of has a bit of a lean, and it hasn't sort of committed to one or the other yet. So it could be either heads or it could be tails. It might be perfectly balanced. It might be 50-50. It could be 80-20. That lean of the coin is what is referred to as superposition. Textbooks will say that it exists in a continuum of states between 0 and 1, but lean is the same sort of idea, and it's something you could probably say at a party and people might understand what you're saying. So the correction that puts you ahead of most science journalism is that it's not 0 and 1 at the same time. If you send a photon towards two paths in superposition and you put a detector on each path, only one detector is only going to fire. There's only one photon. So it just hasn't committed yet to which path it's going down. It's got a lean. Physically, it could be a photon's polarization. It could be an electron spin. It could be atomic energy levels. It could be a superconducting qubit. But you don't have to worry about any of that stuff as a quantum programmer. You don't need to have a PhD in physics because that's what the whole point of abstraction is. Abstraction means that you don't have to understand the underlying physics. The second thing that's important to understand before we move on, yeah, I might say one more thing after that too, is that measurement is effectively slapping the coin flat. So the moment you look at a qubit, the moment you measure it, you've decided whether it's 0 or 1. It can't stay in superposition after you've measured it. So you either measure it after you've built the whole circuit, or you measure it deliberately during the circuit. The numbers under the hood are pretty simple. Most things that make quantum computing hard to understand are math related, but it is actually pretty basic. You know, if you've got a two-sided coin, each side of the coin has an amplitude. Actually, since I've got this set up, I'll quickly draw something. You can see it on the... Thank you. So I'm going to just do a little bit of maths. I promise I won't do much. But this, excuse my shitty handwriting, is how you represent a state of a qubit. So you've just got two values. This one corresponds to 0, and this one corresponds to 1. Alpha is an amplitude. So amplitude is not probability. It's important to understand this. The square of the amplitude is the probability. So that is your probability. So let's say you've got alpha equals 0.707, beta equals 0.707. If you square these and make them absolute values, that then becomes the probabilities, which is just 50-50. So that's all the maths I'm going to go through, but in reality, the maths behind quantum computing is incredibly simple. if you've got an equation in front of you, you don't have to solve the equation. It's just telling you what the probabilities are going to be of your qubits. So we'll go back to the presentation and hopefully get onto some work soon. Gates are just matrices. They're just functions. You apply a gate to a circuit and it just manipulates the qubit. It's really that simple. So we'll go on to our first challenge where you guys can actually start writing quantum code and seeing what these gates do. So let me just push you into the first challenge. It'll tell you exactly what you need to do, but hopefully, has that just put you all into the first challenge? Sick. All right, so just do it practice mode. You don't have to do it competitively. Just give it a go. If you've got any trouble, I'll come over and have a look, or I'll go through the solution on the board probably. The sandbox is public on the full platform. Yeah, so this is, for the sake of it, this is just so you guys don't have to make accounts and that you can sort of mess around with the challenges, but the sandbox is something you can access on the normal website for free. We'll also note that IBM has a similar sort of thing, but a lot of, like, I wasn't planning to put it on the platform, but I had a lot of people say that they wanted it, so I did it, and it makes it easier. I mean, you don't have to set up the API in an IDE or anything. You can just use it in the web platform. So it makes things a little easier. Considering this is the first challenge, I'm going to sort of show you what to do, and then once I've done it, I'll just move on. So, we've already initialized the quantum circuit. So we've already got this variable which sort of represents the quantum circuit. When you want to apply gates to a circuit, it's just a function. And in the argument section, you just specify which qubit you're adding, like you're applying the gate to. So, I mean, that is literally all you need to do. The platform automatically measures the circuit for you, but for the sake of getting in a good habit, it's probably better to just write it anyway. But that's literally, if you got that answer, good work. That should do everything you need. And you can just submit it and we'll move on. There we go. So when you press run solution on that, you're not literally running it on a quantum computer, you're simulating it. And at a very small level, you can run code, quantum code on a normal laptop. The problem is it's an NP problem. As your qubit count increases, the time it takes to process the probabilities increases exponentially. So you do need a quantum computer for large scale problems, but for the sake of learning to program, you can use a simulator, and that is literally how this platform works. I'm just running it on a classical server. And it literally runs the circuit 1,000 times to check what the probability distribution is. So moving on to notation, this literally just means that the qubit is in the state which is labeled 0. It looks fancy. Once you've measured it, it just becomes 0. But this literally just means that it's in a vector state. So the maths behind this stuff isn't that hard. As long as you understand the notation, it becomes easier and easier over time. So I'll introduce you to your first gate, aside from Hadamard. So the Hadamard gate is what puts the qubit in superposition. An X gate is just a quantum NOT gate. It literally just, if you've got a qubit which is in the state of 0 and you apply a quantum NOT gate to it, an X gate, it just flips it from a state of 0 to a state of 1. Where it starts getting interesting with quantum computing is, let's say you have a qubit in superposition where you've got it. Thank you. That'll do the job. So moving forward, it just, what was I talking about? Yes, gates still have error. The less gates you have, the better. So the more efficient you can make your solutions, the less gates you have, the better your circuits are. Yes? Yes. So a qubit, if you think of a coin, so in a normal computer, you've got a lot of little gates. So they can either be a 0 or a 1. A qubit can be in a probability of 0 and 1 at the same time. So it could be 0 or 1, but it could also be 50% likely to become 0 and 50% likely to become 1. Yes, physically. So there are a number of different ways to make quantum hardware. One example of it that you can think of is a photon's polarization. So you could have a photon which is polarized, and then the polarization, like how polarized it is that probability vector. But there are lots and lots of different ways. You could have electron spin. You've got superconducting qubits, which are built with silicon. There are a lot of different ways to build qubits, and there's a lot of competition that's happening between hardware vendors in which one is going to end up being the universal type. And interestingly, I was in Germany last month. The way the researchers over there sort of operate is you do a PhD in one architecture type. So you sort of pick the architecture you want to go down, and that's all you know. Like if you want to go into quantum hardware, you just have to pick one that's going to be your favorite, and that's just going to be your career, because the hardware implementation is so different between every type of qubit. So I encourage, if hardware is what interests you, do some research into it. It's like there's a lot more physics that goes behind it because it's more foundational, but it's certainly an interesting thing to learn about. So what are we moving on to? All right, next one, we'll just apply the X gate, and then you can sort of have a look at the probability of what happens when you do that. So I will force you into that challenge. This one is actually easier than the, oh no, it's not. It's the same level difficulty,
The same number.
same number of characters. But what the interesting thing to look at here is the result you get in the solution. So I mean, I'm sure you guys can all write the code for this. It's not hard. I'll skip the measurement because you don't have to. But if you have a look at the like what actually comes out, you know, you were starting with a gate. You were starting with a qubit which was in state of 0. You've applied the X gate, and now you're measuring 1 with like 100% guaranteed. And it's pretty rare in quantum computing that you'll ever get something that is perfectly the way you expect it to be. If we actually ran this on a quantum computer, you'd have error, and it probably would have a, it would be 99.99%. But the truth is the X gate is incredibly consistent, because it's so fundamentally, like, it's just a NOT gate. So moving on. Well, actually, I'll let you guys. What are we looking at score-wise? What's next? This is what makes quantum interesting. So everything up to this point, we were talking about 1 qubit. 1 qubit is not interesting. What makes quantum start to get kind of spooky, as Einstein likes to refer to it, is entanglement, which only happens if you have a minimum of 2 qubits. So let's say you have 2 qubits. You've got 4 possible readouts. If they're either fully 0 or fully 1, and that's 0, 0, 0, 1, 1, 0, 1, 1. And with a superposition of both qubits, it can lean towards any of those values. So now, rather than having 2 states, you've got 4 states. Doubling it is, if you keep doubling the number of, if you keep adding extra qubits, you're going to double the number of combinations. So it sort of just keeps squaring, and that's the NP problem that I was talking about earlier. So the gate that starts making these things interesting is the C0 gate. So the C0 gate is just an if statement. It's written as QC.CX 0, 1. So then that's just saying your control qubit is your first index, which is 0 because it's 0 indexing, and then your target is 1. And all that does is it flips the second qubit if the first qubit is 1. So it's just an if statement. But where that sort of starts getting interesting is, let's say your first qubit has superposition. Then if you have a C0 gate between your first and your second qubit, you've sort of got an interesting outcome here. I'll draw it out. So back to that again. So you've got 2 qubits, right? So your first qubit is spinning. It can either go to 0 or 1. If it goes to 1, this is going to set, I'll label that 0 and I'll set this one to 1. This one is going to become 1. And if it goes to 0, it's going to go to 0. But let's say there's a 50% chance of either happening. This now creates a new state, because it's not like, once you've applied this gate, you haven't measured the qubit. So this qubit now, this this index of 1 is now in a 50% chance of being... Oh, that's frustrating. What a shame. I might use the pen then. All right, let's do this. So if this goes to 1 and if that goes to 0, then that will be in a state of 1 and this will be in a state of 0. Okay, so this creates an interesting scenario because now, since we haven't measured anything, this one could either be in a state of 0 or 1. So we've now got a 50% chance of either of these outcomes happening. So we've got a 50% chance of this happening and a 50% chance of this happening. So that the outcomes of the qubits are sort of correlated, considering like we're not doing anything to this qubit aside from connecting it to this one. So this outcome, whether the second qubit ends up becoming 0 or 1, is caused by this one either being 0 or 1. So that creates a state called a Bell state. And all that means is you've now got a 50% chance of, well, 25% chance of all of the outcomes happening. So this is sort of where things start getting a little bit spooky because the outcome of the second qubit will change based on the first one, but you haven't touched the second qubit. So they sort of become intercorrelated. So a more, I guess a metaphorical way of describing this is that entangled qubits are like a pair of magic coins. If you toss them together, they'll always land the same way up, but whether they go heads up or tails up is completely random. So regardless of how far away your qubits are, whether you've got one in the US and you've got one in Australia, and you both flip them at the same time, they're both going to end up landing the same way, but there's no way of predicting which way they're going to land. Einstein called this spooky action at a distance. He thought it was fake and that this was all bullshit. But he thought that the theory was incomplete. But what's really strange about this is that if typically in classical physics, if two things are correlated and the outcome of two things are the same thing, then you have to believe, well, it's proven that they probably either compared notes beforehand or they're communicating. But it was tested in 2022. Bell's theorem got a Nobel Prize, and it proved that it is neither comparing notes beforehand or communicating. I won't go much further in that because I sort of want to keep doing keep doing challenges because we're sort of short on time. But as we sort of move to this next challenge, I'll keep talking while you give it a crack. There it is. I should probably create a search for this. Ah, there we go. You are the goat. So while I'm on the topic of entanglement, you can't build entanglement out of single qubit gates. You have to have it applied to two gates. And it sort of kills the sci-fi. Like when you start talking about this, you probably start thinking, well, if the outcomes are going to be the same instantly, no matter how far away it is, can we communicate? Can we send messages? you can't send messages with entanglement because there's no way of knowing which way it's going to land. You can't force one coin to land a certain way and then the other one to land as well. They just will land in a random way, and they just happen to be the same. But there's no way of really communicating anything if your outcome every time you do the experiment is going to be random. Entanglement is the working resource behind quantum cryptography, quantum information. Yeah, so it's the thing that makes quantum computers useful. It's only 2 lines of code. Can probably smash it out now. I also, I deliberately built a trap into this challenge, but I think the platform sort of enables you to cheese it. So typically when you build a quantum circuit, you have to instantiate a circuit first. But if you forget to, it'll work anyway. Despite this, I have had people who've done the previous challenges, and because they only expect that it's going to output 1 qubit. I mean, what this literally means is it's just saying we're going to create a quantum circuit with 2 qubits and then a certain number of classical output qubits. For this to work, you need to have 2 of both because you're going to have probability states on both of your qubits. So we just put it in superposition first with the Hadamard gate, and then we link them together. The syntax for this is just 0 and 1. And I pray that this is going to work. Yippee. Okay. So that has just entangled 2 qubits together. If we go down here, you've now got a 50%. Either they're both going to be 0 or they're both going to be 1. They can never be, they can never have different results, which is what I spoke about. Yo, people are getting a lot more XP than I expected. I think people are doing more challenges than the ones I'm putting up. It's the time, 5:50. Okay. I'm going to briefly explain an actual algorithm rather than just random circuits, because I think everyone would much rather learn about how actual algorithms are built than just random circuits. So I'll introduce you to the Deutsch algorithm, which is actually pretty useless, but it was the first algorithm that proved that quantum computing could be superior to classical computing. So I'll introduce you to a problem. I'll draw on here because we're having problems with my iPad earlier. Actually, where's the... So let's say you've got 2 qubits which go into a black box. We don't know what the black box is. That's the whole point of the algorithm. So this box could either, like, you could send a 0 in here, you could send a 1 in here, and it will either output a constant value, which means that regardless of what you send in, it's going to output the same thing. So you could send in a 0, it'll output a 0. You could send in a 1 and it'll output a 1. It'll output a 0. The reason it's called constant is because it will always constantly do the same thing. I mean, you could also say that it could output 1 all the time. A constant output of the black box means that it will always, regardless of your input, will have the same output. So that's one type that we could be thinking about. Or it could be balanced, which means that you will either, if you send a 0 in, it will either output as, like, it'll output something different than what you put in. So, sorry, it won't output something different than what you put in. it will change its output depending on what you put in. So that could do that, but it could also do the opposite. So our whole goal of the algorithm is to figure out whether the black box is a constant function or a balanced function, i.e., I mean, we've got the potential options up there, whether it's going to have the same result or it's going to have a different result depending on your input. Typically, with a normal computer, you'd have to send 2 inputs in to know, because let's say, I mean, with these states here, I'll actually use my mouse because I don't just want to be standing around like this. If you send a 0 in and you get a 0 out, it could either be constant or it could be balanced, because there is an outcome where you'll get a 0 in and a 0 out. The only thing that differentiates these two is that then when you send another one in, when you send a 1, you're going to get a different result. So with a normal computer, you have to run the algorithm twice, but with a quantum computer, you can do it in one step. I'll explain how the circuit's constructed. I won't explain the details hyper specifically of how it works, because it sort of is out of the scope of the workshop and starts getting into maths that's going to take us a bit of time to get through. But the idea is you put, rather than just sending 1 in at a time, you send 2 qubits in at the same time. So we've got 2 qubits. You apply superposition to the first qubit, which means that it's now going to be in a probability state. It's either 50, 50, 50. Then with the second one, you do the same thing, but you also then apply an X gate to it. Actually, sorry, it's the other way around. You do the X gate first. So all the X gate does, to remind you of what the X gate does, is it turns this 0 and turns it into a 1. So we're now going, rather than trying a 0 and a 1 at different times, we're just going to try them both at the same time. And yes, if you have a multi-threaded CPU, you could do the exact same thing. But the idea is the equivalence of the quantum circuit is that you're only dealing with effectively a one-threaded, you're dealing with a one-threaded processor. You then apply superposition out and then measure both. And I'll move on to the next slide because this will provide some insight into what ends up happening. I know the X gate isn't there, but if you have a look at the label, it says 1. So it's the same thing. If it's a constant function, you're going to get a 0 out. Actually, you don't need the second measurement gate, that's true. If it's constant, you'll get a 0 out. And if it's balanced, you'll get a 1 out. Now, there's a little bit of detail into why this happens. The reason this happens is because when you send the 1 and the 0 in together, this gate ends up entangling the qubits together. And because they have opposite signs, you end up with the coin. These are the results you could get. You could either send a 0, 0 and then a 1, 0. And because they both end up as 0, you don't stamp a minus sign on. If they both end up as 1, you stamp a minus sign on. So to explain this simply, because I'm sort of yapping without aim here, if you get a 0 as an output on one of the qubits, you're going to put a plus sign on that qubit that corresponds to it. If you get a 1, then you're going to put a minus sign onto the qubit that you got a 1 from. So if it ends up being that you get the same sign, either 2 positives or 2 negatives, you're going to get 0. And the reason why that happens, it's referred to as interference. So can I get a show of hands? Has anyone done high school physics? Okay, that's pretty much everyone. So if you haven't, hopefully I can explain this in a way that makes logical sense. Let's say you've got two waves. Sine functions. Well, sine functions, one with one phase and one with the opposite phase. We're going to say that this one here, the one that sort of goes like this, that corresponds to a positive, and then the one that goes in the opposite direction is a negative. If you think of combining those two waves together, let's say every single point on these waveforms you add together, if you do that, what function are you going to get? Yeah, exactly. You're just going to get a straight line, which in this instance results like you'll just get 0. But let's say you get the same function. So same sign, let's say you get the same sign on both. So it could be 2 of these or 2 of these. If you add them together, you're just going to get a bigger wave. Now, I'm going to ask a question. If somebody doesn't have the answer, that's fine. Why is it that when you combine them together, you just get 1 and you don't get 2? Exactly. So in a quantum circuit, you always need, like, all of your probability is always going to add to 1. You can never have a 200% probability of something happening. It's going to add up to 100%. So when you superimpose the waves together, it's just going to end up, your resultant circuit is going to end up being a probability that adds up to 100%. So, I mean, I've shown you the circuit here. I wonder if you could remember it. Let's see. I'll push you into doing the challenge now. You can give it a crack. So this is an actual quantum algorithm. I've got a few of them, so I hope I select the right one. Use the oracle. Okay. There's one thing that, like a little bit of syntax that you won't have learnt from any of this that I'll provide you to sort of make things easier in constructing the circuit. Actually, I'll just write it here. So the oracle is what the black box is. Just make sure you include that line in your code. So that line is what creates the this. So anything to the left side of it, do before it, and everything to the right side of it, do afterwards.
It's still wrong. It is.
A lot of technical problems.
Oh, well, yeah, this is what happens when we haven't charged anything since Game Jam.
Yeah. When was Game Jam?
Week 9, last set. 10.
Yeah. Well, that explains why it's gone flat. Yes. Yeah, absolutely. keep in mind this qubit is a 1, so you're gonna need an X gate as well as the Hadamard's. All right, I think that's roughly enough time. I'll just put the answer in and you guys can sort of see what ends up happening. Okay, so this runs 2 tests on your code. It first tests whether, if it has a constant oracle, whether it's going to output 0 as it expects. If it's got a balanced oracle, then it outputs 1. And you'll see that every single time, 1,024 times it's tested it, it's correct. So that's the first algorithm that was ever constructed to show that quantum computing is potentially superior to classical. It's not useful, as I said, but it is fundamental to understand this to get to actually useful algorithms such as Shor or Grover. Shor is used for cybersecurity. Grover is just a general searching algorithm that speeds up searches. Shor is not a concern at this stage, but when we get a fault-tolerant universal quantum computer, which Google and PsiQuantum estimate to be 2029, it's pretty much going to break cryptography as we know it. Because the whole reason why our passwords are secure is because it takes too long to guess passwords. But quantum computers, if they use Shor's algorithm, can. So just wait until that happens. Post-quantum cryptography is a huge talking point at the moment, particularly in the blockchain space. So if you're interested in cybersecurity, reading up about it would be pretty cool. I was going to start talking about the applications, just sort of to wrap things up. But yeah, these are sort of the known applications at the moment. You've got portfolio optimization, logistics routing, drug discovery, energy and batteries, pretty much anything molecular related, root related, anything where you've potentially got a problem which gets exponentially harder to solve the more options you have. Quantum computing is a potential solution for it. That's why there's so much investment going into it, because a lot of people think that it will be handy for AI. There is no conclusive proof at this stage whether it will be useful for AI, but time will have to tell. Scientists will tell you it's not going to be helpful for AI. VCs will tell you it will be. I sort of sit on the fence. Hopefully it will be. I think being optimistic and dreaming of the potential possibilities is how we sort of progress forward and do things that are innovative. So I think people were just doing random challenges throughout all of that. Good job to Rio if Rio is here. Pretty good result, 5,300 XP. I think we'll wrap up. Is Pizza here yet?
Yeah, should be. Committee's getting that set up outside, so yeah.
Okay.
Take time for questions and wrap up.
Yep, sure. So I will end this. If you want to mess around with Qubit Forge, this is going to prompt you to create an account. It is free. So, you know, I'd probably recommend just making an account and you can mess around with it whenever you want. In a few months, my goal is to release an app, sort of Duolingo inspired, where you sort of spend 5 minutes a day learning little quantum tidbits, enough. I mean, the idea is for the platform to pretty much make you job ready. So rather than doom scrolling for like half an hour, spend at least 5 minutes of it learning about quantum computing. That's pretty much all for today. Does anyone have any questions about quantum generally or anything I spoke about? No? Cool.
I do have one.
Yeah, you do?
I'm just personally curious about how you actually got into the space itself, because you did say it was hard to find papers and stuff like that they were digestible.
Yeah.
Are there any resources that you recommend for anyone interested out there for quantum computing?
Yeah.
That they could pick up,
Sure. So
including a platform, of course.
my platform was really the solution I built to make it easier. There are a lot of really good books in the space. Like if you are a reader and you like reading, which I think a lot of comp sci people probably are, there's probably 2 books I'd recommend. There's, I think it's called Quantum Computing for Everyone. I won't write it. I think you can. I think you can remember that. Yeah. The author's name I think is Bernhardt. And then there's also a textbook called Nielsen and it's made by Nielsen and Chuang. And as I said earlier, it's sort of the Bible in the field. But Quantum Computing for Everyone teaches you the maths behind a lot of quantum computing and introduces you to a few of the algorithms. And then there's also a book called Computing with Quantum Cats, which sort of goes over the history of computation, sort of in a more abstract lens, and what quantum computing could do in the future. So either of those books and then the textbook Nielsen and Chuang is probably what I would recommend. Yep.
Because I don't know if this is like actually a decent one.
Mm-hmm.
It's a bit like quantum like computing hardware. Each of those squids are like something way more complex than that.
When I refer to quantum computing hardware, I'm referring to the chip fabrication that's being done to construct chips that can sort of represent qubits. Does that make sense?
Yeah.
So sort of it's been thought of for a very long time that if you wanted a quantum computer to function, you'd have to develop completely new infrastructure for how our bits are represented. Like you can't have transistors anymore. So we need to figure out how we're going to actually store data, how we're going to process data, like what are our new transistors in quantum. So a lot of different people are trying different things out. What makes PsiQuantum so cool and why it is so cool we're close to them is they're building it on actual silicon. So most qubits are made with really rare earth minerals and it's super expensive. But PsiQuantum is doing it on silicon, which means that we can use our existing chip fabs. Like we can use the same factories to make quantum hardware, which is really exciting. And hopefully that'll get us to 1 million qubits faster than it would have been otherwise. Any other questions?
Another question that I was discussing with people about how, I was thinking in terms of like randomness, it would be more random using qubits than just normal ones and zeros.
Yeah.
But I feel like it would be more towards the goal of complete randomness rather than.
Well, it literally is completely random.
Yes. So it's all PRNG is what?
Yes.
Oh, okay.
Yeah. So, I mean, just to sort of fill you guys in, if you don't sort of understand what the context of that was, with classical computing, there's sort of a problem where if you want to produce some random number, you can't really provide anything that's truly random, because the way computing works is that a computer will take an input, it will do a sequence of steps on that input, and it will then produce an output. So the process is consistent, and ultimately, yeah, there's a lot more to it than just that. But yeah, the idea is with a normal computer, you can't get anything truly random. But with quantum computers, you can, because the underlying physics is random.
And is that because of what is it, the completely random integers, like of it being either 1 or 0?
Yeah, the whole idea is when you put a qubit in superposition, that it can be.
And it's always like it's not going to be exactly like 0.2 of 1 or and then the 0.8 of 0. Like it can be infinitely.
Yeah.
Yeah. Okay.
Well, it depends how you construct your circuit.
Yeah.
you can make it 50-50, you can make it 0.2, 0.8, depends on how you manipulate your gates.
So it doesn't have to be like exact fractions.
Yeah.
Okay.
Any other questions from the room?
Yeah, what companies are hiring quantum programmers, seeing as we can only run it on 12 quantum computers?
Yeah, so quantum programmers are largely being brought in, like PsiQuantum has positions for quantum information science. Companies like JP Morgan, Goldman Sachs, so you've got banks, there are a lot of startups that are coming up with like algorithmic solutions to things, so you could get a job at a startup. But yeah, a lot of the hardware providers, I mean, even NVIDIA maybe, like NVIDIA, IBM, Google. So there are a lot of programming jobs available. Those programming jobs will increase as we get better quantum computers. But because there are still pilots that are being operated at the moment in molecular research, in financial, like why I say JP Morgan and Goldman Sachs is because there's a lot of pilots being run in share portfolios and how we optimize our share portfolios. So interesting, you've got quant and quantum sort of together, which could be cool. I think that's everything. And no more questions? Cool.